Welcome to AI Paper Slop. We are jumping straight in today.
Let's do it.
So the paper is Xiaomi-Robotics-U, Unified Embodied Synthesis with World Foundation Model. And if you were an ML engineer or, a researcher working in embodied AI, this is the core takeaway you need right now.
Right up front.
Yeah. Xiaomi has built a 38 billion parameter multimodal autoregressive model that, well, it effectively solves the catastrophic forgetting bottleneck in robotics.
Which is huge.
It is. By jointly training on general internet-scale visual data alongside strictly calibrated robotic, multi-view, and geometric data, it functions as a unified world model.
A true world model, yeah.
And for inference, they achieve an 82.9x speedup using an anti-diagonal decoding method called FlashR plus EchoM. Plus, they proved its value by boosting real-world, out-of-distribution robotic policy success rates from 36.9% all the way up to 63.2%.
Which is just a massive leap. And your mission for this deep dive into the research is to understand the actual mechanics behind those numbers.
Exactly.
We are going to unpack how Xiaomi avoided the trap of specializing a foundation model into this rigid, robot-only generator. We'll look at how they turned it into a highly scalable, zero-shot data engine.
Because it can generate infinite, geometrically coherent robotic training trajectories without losing its broader semantic understanding of the world.
Yeah, that's the key. But to really appreciate the architecture they built, we should probably establish why current foundation models are failing us in physical robotics.
Right, because we have these massive, highly capable models now.
Oh, absolutely. I mean, they can generate hyper-realistic, high-definition videos of complex scenes from a simple text prompt.
But the moment you try to apply that same generative power to an embodied scenario like a robotic arm attempting to grasp a physical mug in a 3D space, the utility of that generated data just plummets.
It drops completely because the baseline requirements are fundamentally different. I mean, natural image or video generation just have to trick the human eye, right, into thinking something looks plausible.
Right, a warped shadow doesn't matter.
Exactly. A subtly shifting perspective in an AI video doesn't break the illusion for a casual viewer, but embodied generation requires mathematical, strict, multi-view consistency. It demands physical coherence across different camera sensors.
Because the robot is literally calculating joint angles based on that visual data.
That is the core constraint right there. If you have a left wrist camera and a right wrist camera, the target object's position, scale, and occlusion must perfectly align with the robot's kinematics in 3D space.
Otherwise, things go bad quickly.
Very bad. If a foundation model generates a synthetic training scene where a cup is, say, 10 centimeters from the gripper in the left camera view, but mathematically 12 centimeters away in the right camera view.
Good man.
Yeah. A downstream manipulation policy trained on that data will calculate the wrong motor torques. It will crash into the table or just miss the object entirely.
It has to be compatible with precise robot control, not just visually realistic to a human. And the flawed status quo to fix this has been taking these massive foundation models and fine-tuning them exclusively on whatever small, pristine, robot trajectory datasets a lab happens to have.
Which, I mean, it seems logical on the surface.
Right, but you are taking a model trained on the entire internet and feeding it thousands of hours of a gray robot arm hovering over a gray table.
And the result of that approach is catastrophic forgetting. The model is forced to update its weights to minimize the loss on that specific, narrow robotic data.
And it just overrides everything else.
Yeah, in doing so, it overwrites the vast semantic understanding, the diversity of lighting, the complex textures, and the broad visual reasoning it originally acquired during its pre-training phase.
It's like taking a brilliant polymath who understands all of human art, physics, culture, and forcing them to only study factory assembly lines for 6 months until they literally forget what a tree looks like.
That is exactly it. You trade a vast understanding of the world for a microscopic understanding of a single lab bench.
So how does Xiaomi prevent this polymath amnesia?
Entirely through their architecture and a unified training objective. This brings us to the model specs for Xiaomi-Robotics-U0. They initialized it from EMU 3.5,
Okay.
which is built on the Qwen 332B decoder-only transformer. And to handle the visual inputs, they utilized an IBQ tokenizer with a 16 by 16 spatial compression ratio.
Let's break down that tokenizer choice for a second because that's important.
Sure.
An IBQ tokenizer with a 16 by 16 compression ratio essentially means they're taking massive high-resolution visual inputs, multiple camera feeds, depth maps, and mathematically compressing them spatially.
Right, converting patches into tokens.
Yeah, it converts 16 by 16 pixel patches into single discrete tokens. This is crucial because if you fed raw, uncompressed pixels from multiple cameras into a 38 billion parameter model, the compute requirements would choke immediately.
Oh, it would be impossible.
Wow.
The tokenizer shrinks the sequence length while retaining the exact geometric layout of the scene. And once that data is tokenized, they diverge from conventional embodied world models entirely. Well, usually, if you want a model to perform distinct tasks, you bolt on task-specific prediction heads. You have one neural network head for text-to-image generation, a separate head for predicting the next robot action, and maybe another for analyzing depth.
Right, a very compartmentalized approach.
Exactly. Xiaomi threw that paradigm out. They treat absolutely everything, text-to-image, any-to-image editing, embodied scene generation, cross-scene transfer, multi-FPS video generation as a single autoregressive sequence.
So they're forcing every single modality to speak the exact same underlying language of discrete tokens.
Yep. It is all just next token prediction in a unified vocabulary. And that unified objective acts as a really powerful regularizer.
Because it's seeing all the data together.
Precisely. By continuously co-training the model to generate general internet images right alongside robotic multi-view images, the model learns that a robot arm is simply another physical concept operating within its massive pre-existing world model.
Okay, I see.
The general text-image data continuously reinforces its broad visual priors, while the embodied data teaches it to synthesize physically plausible initial robot observations and interaction dynamics.
So it isn't sequential fine-tuning, where it forgets the old stuff. It is simultaneous co-training.
Exactly.
It is an elegant architecture, but, I mean, a unified token space is completely useless if the data you feed it is biased or improperly formatted, right?
So garbage in, garbage out, absolutely.
Because a robot's raw telemetry data looks absolutely nothing like a text prompt or a compressed JPEG. So how did they keep this decoder-only transformer from getting entirely confused by the formatting?
The scale of their data engine is staggering, honestly.
Yeah, looking at the numbers, it's 9.5 million single-step samples. That's 56.4 billion tokens, plus 2.6 million video clips, adding another 49.6 billion tokens.
And the secret lies in the diversity of those domains and how rigorously they structured the annotations. They didn't just dump raw robot data into the training pool.
They curated it pretty heavily, right?
Yeah, very heavily. 6 highly distinct domains to build a comprehensive worldview. They used general image text data from shared GPT-4V to maintain semantic alignment. Then they utilized embodied manipulation data from sources like Agibot World Beta, OpenX Embodiment, and their in-house MyBot dataset to teach physical interaction.
I noticed they also brought in autonomous driving data from Cosmos Drive Dreams, which at first glance seems out of place for a model designed to help a tabletop robot arm fold a towel.
It does seem weird, right?
Yeah, but when you think about the underlying physics, autonomous driving data is incredibly rich in exact geometric depth, spatial reasoning, and tracking dynamic objects moving through a 3D space.
And that spatial reasoning is exactly why it was included. A tabletop robot needs to understand depth and object permanence just as much as a self-driving car does.
Makes total sense.
And to further reinforce that, they included egocentric data from EgoWalk to capture first-person perspective and human motion patterns. They brought in 3D reconstruction data like Scanet++ for dense multi-view correspondence and accurate room geometry. And finally, game data from OpenP2P to expand the visual distribution far beyond what real-world cameras capture.
That is a massive, heterogeneous mess of data. You have raw driving videos, precise robot telemetry, static internet images, simulation data. Standardizing the supervision signals across all of those formats requires a massive automated pipeline.
It really does. So Xiaomi built a unified annotation pipeline utilizing the Qwen3 VL235B vision language model to generate dense structured annotations for all of it.
Wow, using a 235 billion parameter model just for annotating the training data.
Yeah, the compute is wild. But for the embodied manipulation data specifically, they didn't just ask the vision model for a simple caption like, robot picks up cup.
Right.
They forced the model to mathematically decompose the scenes into 5 orthogonal semantic dimensions: the workspace, the task objects, irrelevant foreground objects, the lighting, and the background.
Okay, that disentanglement right there is the entire secret to their zero-shot generation capabilities later on.
You nailed it.
By forcing the vision language model to annotate the lighting entirely separately from the object itself, The world model mathematically learns that a cup remains a cup, regardless of whether it is sitting in a pitch-black room, bathed in harsh sunlight, or sitting under a red LED.
Exactly. It untangles the specific pixels of the object from the pixels of the environment. And then they took that structured data and paired it with geometric conditioning signals.
What did they use for that?
They used a model called video depth, anything to extract temporally consistent inverse depth maps from the videos.
Oh, okay.
And they also had to address the temporal structure of the robot data because, a 10-minute video of a robot task is mostly empty time, just sitting there. So they applied HGBS scan clustering to the robot's end effector poses and gripper signals.
And for those unfamiliar with the algorithm, HGBS scan is a density-based clustering tool. So instead of manually watching hours of video to find the moment the robot actually does something,
which would take forever.
Right. They feed the raw telemetry coordinates of the robotic arm into HGBS scan. The algorithm looks for dense clusters of data points, like the gripper slowing down, adjusting its angle, closing its fingers, and it automatically segments a long, boring trajectory into distinct, actionable subtasks. Reaching, grasping, moving, placing.
Which directly enables their aggressive data balancing strategy. If you just train a model on raw robot logs, you run into severe domain bias. 80% of the data might just be the gripper hovering over a table doing nothing.
Yeah, if you train on that, your 38 billion parameter model will become an expert at generating a whole lot of nothing.
Precisely. By clustering the actions, Xiaomi actively downsampled redundant static trajectories, and they deliberately upweighted the long tail categories.
So the tricky stuff gets prioritized.
Yeah. If a clip featured a rare object, a complex manipulation skill, or a dense interaction phase like the exact millisecond of a tricky grasp, they forced the model to focus its learning on those complex physics transitions, not the empty space.
So we have a beautifully curated, massively balanced data engine feeding into a unified 38 billion parameter model. But for the ML engineers listening who actually have to deploy these systems, this raises a glaring practical issue.
The inference speed.
Exactly. If this model is meant to act as a scalable engine to generate synthetic training trajectories for real robots, it cannot take 10 minutes to generate a single visual frame. Standard autoregressive generation is inherently serial. It predicts token by token.
And at high resolutions, that serial process is an absolute bottleneck. The researchers noted that at a 124 by 124 resolution, standard raster order autoregressive decoding, so predicting every token individually, was taking them 450.77 seconds per image.
That's over 7 minutes. You cannot simulate millions of hours of robotic worlds to train downstream policies if it takes 7 minutes to generate a single frame of data.
You really can't. So to shatter that inference bottleneck, they introduced FlashR plus Plenty. They completely abandoned standard raster order decoding.
To visualize standard decoding, think of it like reading a book. You go one word at a time, left to right, line by line. Anti-diagonal decoding, which FlashR Plus uses, is more like a team of tile layers, tiling a massive floor.
Oh, I love that analogy.
Yeah, instead of one person laying tiles row by row, an entire team starts at the top left corner and lays tiles diagonally outward in a continuous parallel wave.
And to execute that wave computationally, FlashR Plus introduces a horizontal head and a vertical head with gated fusion. This architectural tweak allows multiple visual tokens along a diagonal axis to be generated simultaneously by the model.
Okay.
Furthermore, they paired this parallel generation with VLLM, which provides optimized KV cache management.
Right, and the KV cache essentially manages the memory footprint of all previously generated tokens, preventing the GPU from constantly recalculating past states and allowing for continuous batching of requests. But hold on, I need to push back on the mechanics of that tile-laying metaphor.
Oh, go for it.
If you are predicting multiple tokens at the exact same time across a diagonal, isn't the model going to leak future information? Autoregressive models rely on causality. Token B needs to know what token A looks like to make sense.
Right.
If tokens are generated simultaneously in a parallel step, how does the model maintain causal structure and keep the spatial conditioning from the reference images without getting totally confused?
That is a great question. The structural integrity is maintained through a prefix condition step causal mask. Think of the input sequence for a generation task. You have your text instructions, your reference images, and your depth maps.
Okay, Tos.
All of that foundational data is treated as a fully visible conditional prefix. The tokens being generated for the new target image can freely attend to all of that prefix data normally. The reference images are completely unmasked, so their semantic and spatial data is perfectly preserved.
Okay, so the context is fully visible to everything being generated.
Yes. But within the target image itself, the new tokens being generated, they apply a strict step causal mask. A token being generated on a specific anti-diagonal step can only attend to tokens from earlier anti-diagonal steps.
Oh, I see.
The key is that tokens generated in the exact same parallel step are mathematically masked to be mutually invisible to each other. They cannot cross-reference their parallel peers, which strictly preserves the autoregressive causality.
That makes a lot of sense.
It allows them to achieve parallel generation speeds without sacrificing the structural conditioning required for robotic geometry.
And the combination of the parallel decoding and the KV cache management drops the latency from over 450 seconds to just 5.4 seconds per image.
Yeah, an 82.9x speed up.
Which makes it actually viable as a synthetic data generator.
Yeah.
So let's move from the theoretical architecture to the physical validation. Does this unified model actually outperform state-of-the-art vision models, and does it meaningfully improve physical robot policies?
They benchmarked it heavily, starting with a direct evaluation against GPT Image 2.0 on embodied transfer and multi-view scene generation. And GPT Image 2.0 is arguably one of the most capable models available.
For sure.
If you prompt it for an image, the output is stunningly photorealistic and visually coherent.
But visual coherence is not geometric coherence.
Exactly, the problem. The researchers documented that in multi-view scenarios, GPT Image 2.0 hallucinates terrible cross-view geometry. It treats the different camera views as essentially independent generations.
Oh, wow.
It will place objects at inconsistent distances across the left and right cameras, warp the surfaces of tables, and just fail to create a mathematically coherent 3D scene. Xiaomi-Robotics-U0, constrained by its multi-domain training and depth conditioning, perfectly preserved the multi-view depth.
Which sets the stage for the physical robot tests. They deployed this on a bimanual ARX robot platform. This is a real-world dual-arm setup with two 6-degree of freedom arms.
A very standard, robust setup.
And they tested it on 3 complex tabletop tasks: store your phones, fold towel, and pack box. I want to highlight that these are not trivial tasks. A towel is a highly deformable object with complex physics that change every time you touch it.
Oh yeah, folding a towel is famously hard for robots.
And storing your phones requires precise spatial insertions.
So to execute those tasks, they trained a standard Pi 0.5 vision language action policy. For those who might not work directly with control policies, a VLA policy like Pi 0.5 is a model specifically designed to take in raw pixels from the cameras and text instructions and map them directly to continuous motor commands.
So the literal joint angles and torques required to move the robot.
Exactly. They started by establishing a baseline. They trained the Pi 0.5 policy strictly on standard, clean demonstration data gathered in a controlled lab environment. Under those pristine conditions, the robot performed the tasks reliably.
But physical reality is rarely a pristine lab.
Never is. When they introduced interference conditions during testing novel, held out tailor clock patterns, low lighting, dramatically different colored lights.
And didn't they use an actual disco ball throwing harsh, moving light artifacts across the workspace?
Yes, the disco ball test. And under those conditions, the baseline policy completely fell apart. The success rate plummeted to just 36.9% task completion progress.
Ouch.
The downstream policy simply couldn't parse the visual artifacts. It saw a disco ball reflection on the table and hallucinated it as a physical obstacle, or it lost track of the towel's edges against a new patterned background. It lacked visual invariance.
This is where the payoff of Xiaomi-Robotics-U0 becomes entirely clear.
Yeah.
Because they had mathematically disentangled the control dimensions during training, separating the lighting, the background, and the objects they could use U0 to take the original clean robot trajectories and zero-shot transfer them into entirely new synthetic environments.
That's the magic trick. They utilized the world model as a hallucinated simulator. They fed the original robot states into U0 and prompted it to generate identical trajectories, but swapped the backgrounds to complex patterns, altered the textures of the table, and applied harsh, chaotic lighting variations. Because of its geometric conditioning, U0 perfectly preserved the exact kinematic state of the robot arms and the positional geometry of the towel and the earphones within these wild new visual environments.
So they took this newly generated, highly augmented synthetic dataset and used it to train a new Pi 0.5 policy. And when they threw that augmented policy back onto the physical disco lights and novel backgrounds, the success rate skyrocketed to 63.2%.
Almost double the performance in outer-distribution tests. The physical robot learned true visual invariance because the world model functioned as a flawless, geometrically coherent training simulator.
It exposed the control policy to infinite visual edge cases without requiring a human to manually teleoperate the robot under a disco ball for hours.
Nobody wants to do that. And that performance leap signifies a fundamental shift in how we approach embodied AI. Foundation world models have officially crossed a threshold.
They really have.
They are no longer just passive video generators creating visually appealing content for human consumption. Xiaomi-Robotics-U0 proves that these models are now robust, structurally sound, interactive physical simulators. They can synthesize endless, highly diverse, temporally coherent training trajectories that directly and dramatically upgrade real-world downstream policies.
So for the researchers and engineers out there building the next generation of physical agents, this means the data collection bottleneck is finally cracking. We are actively moving from a paradigm of manually collecting thousands of hours of tedious robot teleoperation to generating millions of hours of synthetic, physics-aligned experiences in a fraction of the time using accelerated parallel decoding.
And looking at the trajectory of this research, it leaves us with a highly provocative question to consider.
Lay it on us.
If an autoregressive foundation model can perfectly simulate multi-view, geometrically precise, interactive robot dynamics simply from a text prompt and an initial state image, well, are we rapidly approaching a threshold where robotic hardware becomes a secondary concern?
Interesting.
We may soon reach a point where physical agents will master their entire control policies across millions of edge cases, entirely inside hallucinated digital world models before their physical motors are ever powered on for the first time.
That is a fascinating threshold to think about the next time you're waiting for a real-world data collection script to finish running. That is all for today's deep dive into the source of material. Thanks for listening to AI Paper Slop, and we'll catch you on the next one.